Welcome to my new calculus channel. My name is John Gabriel, and in this final video regarding the ZFC axioms, or beliefs rather, I will be discussing the so-called axiom of choice. Now this one is the big one, and I must tell you that this is not an axiom. It's not even a logical belief, in fact. But at any rate, without further ado, let me start talking about it. And this is going to be a slightly longer presentation because there is so much more to cover. So let's begin. Now, as you've seen in the past videos, I've explained to you how you can break every single one of the ZFC axioms, because they're not really axioms, they're beliefs. And you'll also note that in axiom or belief 6, I showed you how there is no definition of set or element. There never is any definition, but one determines whether a given object is a set or an element using the ZFC beliefs. Okay. So now, the belief of choice states that every family of non-empty sets has a choice function. Well, what it really states is that you can pick an element out of any non-empty set, okay? In other words, you can just close your eyes and pick an element, provided the elements are well formed, okay? That's the whole idea behind this axiom of choice. The idiot Zermelo was attempting to do a lot more than just what he did in the axiom of replacement, where he put together the decrees and rules for functions and mapping. So what he wanted to do was make sure that you could map an infinite set, which doesn't exist, to another infinite set, okay? Which really means that if you have a curve, like let's say y is equal to 1, in other words, you want to be able to, he wanted to be able to say that this line here is continuous and is defined for every mapping. However, while you may turn around and say that's true, it's not actually true if you're talking about mapping of numbers. It's true if you're mapping distances, okay? So in other words, if you're talking about distances along the x-axis, no problem. You can map that distance to 1. But not every one of these distances has a number that describes it, okay? In other words, there are many magnitudes on this line here which are incommensurable. What that means is they have no measure. But what Zermelo wanted to ensure, and the idiots of the last 100 years in the mainstream, is that you could literally map any of these so-called points to some other point, not even necessarily a line, but a curve of any particular structure or a surface, right? So the belief is written as you see here: for all x is an element of little a, presuming, little a is a set, which means that there exists a function a which takes sets x and y, and you have the implication which appears to the right of this arrow, okay? So this belief is really just a stronger version of belief 6, the belief of replacement. Belief 6 wants you to think that sets can be mapped in a systematic way with discrete elements. However, belief 9 wants you to think that sets can be mapped even with continuous elements. In other words, you have a real number line, which is bullshit. There is no such thing as a real number line. And you can map those numbers, okay? So you cannot choose an element unless you know what it is. So what do I mean by that? Okay, so supposing I tell you to choose a number, to choose an element between the open, to choose an element from the open interval 3, 4, okay, where the open interval 3, 4 is really just this interval as follows. In other words, I just want to reduce this so I can show you exactly what I'm talking about. All right, so here we are. So if we have 3 and 4, so in other words, I want you to pick an element between these 2 points here, okay? So between, let me just move this out of the way, between this point here and this point here, okay? Now, by the way, I'm going to add an extra requirement. You cannot pick a rational number. So in other words, I'm removing all the rational numbers from this interval. So you can't turn around and say, oh yeah, just divide that interval by 2. No, I'm sorry. I want you to give me an element inside here which you can choose. So now the first element that might come to your mind is your so-called irrational number pi. Pi isn't a number of any sort. It's a magnitude which is incommensurable. So then I tell you, okay, well, show me where is that magnitude pi. So you go, you do something like this. You go x is equal to pi, right? Like that. And then suddenly you have this line here, which presumably goes through pi. The problem is it doesn't actually go through pi. It goes through some rational approximation of pi, all right? So we can expand this, and let's do that like so. So, and I can prove to you that even if I say x is equal to 3.14159, like that, you won't be able to see the difference between that line and the other one. And I can also break this line up as follows. I can make it like that. And so the red line over here, I can make that thick as so. Okay, so you can see that it doesn't matter what particular rational number I choose. If it's close enough to the rational approximation that the software uses, then you're not going to be able to distinguish between the lines, no matter how much you open up these intervals, okay? No matter how much you stretch these intervals, you're not going to be able to differentiate between the two, right? This is basically equal to pi, but this number here is not the same as pi. So if I had to say, see that? So in this case here, I said the number here is a line I, and this is an approximation. So even neither of these numbers is pi, right? And in fact, the distance from the origin to this point here, from the origin 0 to that point, is really a magnitude. It's not a number. But now, the idea behind the axiom of choice is that you can actually pick out irrational numbers, so to speak. There aren't any, but you can actually pick out one. The problem with the axiom of choice is that you cannot choose an element unless you know what it is, okay? So, as I've just given you an example, if you retort pi is such an element, well, it's not, because you can't pick it out because you don't know what it is. Okay, so you can't just say, oh yeah, it's this magnitude. That's nonsense. A number describes the magnitude, and you can't call the magnitude an element because you have no name in terms of a number. In other words, your real number line is a myth. There's no way you can calibrate pi, even if you can mark it off, presumably on the line. There's no number to describe that magnitude. And this is where the delusional Zermelo redemption belief comes in, the axiom of choice. That is, as long as there is some sort of function that generates the digits of pi, then you should pretend that you have actually chosen pi. Did you get that? So in other words, if there's a function like a Taylor series or something, or anything else that produces pi, you can presume or pretend that you have actually chosen pi. The fact is that at no time can you recognize any of the elements which you imagine to be irrational numbers, okay? They are not numbers at all. So a magnitude is not a number, and a number describes the measure of a magnitude. So the only numbers in the universe are rational numbers. There are no other numbers. But these morons of the last 150 years in the mainstream have tried to produce valid constructions of real number, but none of them are valid. Diedeker construction is not valid, neither is Cauchy equivalence classes, and neither is Eudoxus, by the way. Some moron, Psi.math, seems to think that Eudoxus formed valid construction of real number, but that's never happened. I'll tell you this, not even God can measure those magnitudes known as pi and square root 2 and e. That's right, not even the gods can do that. So you might look at the graph of a function and imagine that it is complete. However, you will be wrong if you think it is. In other words, if you look at this, this is supposedly a solid line, but the software doesn't actually print that line entirely as you think it does by plotting pixels. It doesn't print it that way. And even the hardware doesn't illuminate the screen at every possible point on the line. It's only pixels of a given size. And so in reality, if you could see very well, you would see holes in this particular line, as you would see on any graph, simply because the software tries to show you that the line is continuous and not broken, but it is broken in terms of the sense that numbers are not available to describe every one of these points, okay? Only magnitudes. Okay, so, excuse me. So while any distance can be mapped to any other distance, it's not so easy to map an incommensurable magnitude. And mapping distances without measure is decidedly not the same as mapping numbers. And of course, as I've just said, no computer software or graphics firmware uses anything but rational numbers, okay? I remember in the old days, back in 1980, if you wanted to put anything on the screen, whether it be a pixel or a number, you needed to know the hardware screen address and then raise the signal by outing the correct value to that port. So if I remember correctly, for a color screen, it was 0B800 hex. That was the address of the screen. Okay, so at any rate, you never ever draw a complete curve. It only appears to be complete because of the way it is being done by the software. So, and as I've just shown you, the line 3.14159 and x is equal to pi will be indistinguishable, and you can only scale up to a certain point. So no software actually draws continuous curves, even though they appear to be. So in fact, what is the crunch of belief 9? It's simply this. The so-called real number continuum requires belief 9. I don't give a crap what anybody who came before me supposedly proved, not what Gödel proved or Cohen, who won the Fields Medal Prize sometime in the last century. Those guys were both idiots, okay? Really, the ZFC axioms require the axiom of choice. Otherwise, you know, their supposed set of beliefs isn't complete. So they're all nonsense, by the way. They're all rules that they've made. And in mathematics, there are no rules. There's only logic and rational thought. You don't get to say, oh, well, in this case, every set contains a subset and you expect everybody to believe you. That's bullshit, okay? You have to prove these things. And there is no proof. That's why these orangutans of the mainstream decreed that from henceforth, those beliefs will be axioms. In other words, an axiom is something that can't necessarily be proved. So from these myths and misguided ideas come the mainstream understanding of number. You know, the real number line, there is no real number line. It's possible to construct a rational number line, but beyond that, you can't have anything. So without belief 6, there is no well ordering, and without belief 9, there is no continuing. There's no continuum. All right, so no continuum without belief 9. The foundations of mathematics are Euclid's elements, not the rot of set theory and ZFC crap axioms, a bunch of ill-conceived ideas. Now, just to finish us off, I want to show you that even up till today, mainstream academics don't know what the hell they're talking about. So if you go to a site like Reddit, you'll see this topic being discussed. So somebody says here, suppose you have a bunch of boxes with random stuff in them. Anyway, I'm not going to read the whole thing out. You can read it yourself. Hit the pause button and read it, or go to the URL, which is right up top there, and then read some of the responses, okay? And I think this one that was made about 5 years ago is really classic. So let's read through this together. It says mathematicians, I call them mathematicians, a few hundred years ago were trying to put together the rules to explain what is a set and what it does and how you can manipulate it, right? At first, it looked pretty easy. A set is a collection of objects. You can do things like take the union and put them, into bijection, or collect the sets and dissect them and whatever, take their intersection, or the power set of a set, which is a set of all subsets of the original set, etc., etc. So all of these ideas, which were the first notions of set theory, did not work. And so he says, yeah, oh, that's right. You can also have sets of sets and sets which are elements and elements which are sets. And sets can be described by a rule, notice this, by a rule, rather than needing to list out all the elements. That's the essence of the axiom of replacement, which is belief 6, okay? So you can have, a set which is described, as you see here, the set of all x such that x is an even integer greater than 0. But that's nonsense. That doesn't describe the whole set. That just describes a particular part of the set, or how to generate the set. But you cannot generate the entire set, because there is no such thing as an infinite set. So you can't just say 2, 4, 6, ... and say that's an infinite set. That's not an infinite set. That's a finite set with 3 elements and an ellipsis, okay? But you can also have a finite set of real numbers, and it says now, and if you got really tricksy, I don't know what that word means, but anyway, you could make a set contain itself. Did you get that? You could make a set contain itself. Don't ask me how, but anyway, like maybe the set of all sets. It's a set itself, so it must be able to contain itself, right? That's, I believe, the mainstream theory that sets contain themselves, but that's bullshit. And then, according to Bertrand Russell, who came along and said that the set of all sets that do not contain themselves is a set, and asked whether it contained itself or not. So what you'll have here is an infinite recursion, and there's obviously no answer to that, because it's nonsense. It leads to the conclusion that if a set contains itself, then it shouldn't contain itself, and if it doesn't contain itself, then it should. So in other words, it's nonsense. And here comes the crunch point. It says, so the only possible conclusion was that it wasn't a proper set. Well, listen to me, you morons. It's either a set or it isn't. There is nothing else in between, okay? There's no such thing as a proper set or not a proper set. It's either a set or it isn't a set. Get it? And that meant that something was wrong with the way that sets was being defined. You don't say. Well, the idiots have never rigorized their foundations of mathematics, by the way. you can break every single one of their so-called axioms. They're not axioms, they're beliefs. And it's easy to make up theory which is going to be paradoxical and contradictory when you base it on beliefs, things that you assume to be true, but you cannot prove to be true, such as infinity, okay? So, and if you read through this thread here, it's kind of amusing because a lot of them don't know what they're talking about. Some of them know a little bit. Some of them have read a lot. And Reddit is basically a very crap site, but it's sometimes amusing to visit. So anyway, this idiot says, that said, to this day, no evidence of its inconsistency has been found. You see, now, this guy here is obviously a brainwashed moron, all right? He doesn't know what the hell he's talking about. Now, and if you go to Wikipedia, you'll see that Cohen showed that the continuum hypothesis cannot be proven from the Zermelo-Fraenkel axioms with choice. Now, I don't really care what it says there, whether it can be proven or not. To me, that statement there is not proof of anything. And the fact that he received a Fields Medal just tells me that the orangutans in the mainstream church of academia simply awarded him a medal because they felt that what he supposedly proved was worth something. I don't think, in fact, I know that whatever Cohen proved wasn't worth anything. And the same goes for Gödel, who supposedly showed that CH cannot be disproved from ZF, okay, even if the axiom of choice is adopted. So at any rate, and the chief crank behind all this was the father of all mathematical cranks, George Cantor. See, you can't have things like Aleph 0 and Aleph 1 and Aleph null without the axiom of choice. In other words, without the belief of choice. So Cantor is really the root evil of all of this. There is no such thing as different level of infinities. There aren't even real numbers, but the morons of mainstream academia haven't realized these things because they were not able to understand Euclid's elements, all right? So in Euclid's elements, we find the foundations of mathematics. And there was no need to recreate the foundations. If they had understood the original foundations, in fact, the provable foundations, because there are no axioms in Euclid's elements, by the way. In Greek geometry, in fact, in geometry, there are no axioms. There is this bullshit about the fifth postulate. There are no postulates. You can derive parallel lines systematically from nothing. Okay, so you start off with an empty universe, then a point, as I've shown in several of my videos and articles that I've written. There are no axioms or postulates in sound mathematics because rules and decrees and faith and belief have no place in mathematics. Well, this has been a rather long presentation. And I'm out of breath now, so I guess it's time to stop. This is a new calculus channel. My name is John Gabriel. Till next time, goodbye.